In the previous lecture, you looked at how to insert values into a binary search tree and how to delete values from a binary search tree. In this lecture, we will look at the concept of balancing a binary search tree and different methods that we can use to achieve this. And the objective behind balancing a binary search tree is to optimize its search efficiency. So, as I just mentioned, we are attempting to balance trees in order to optimize the search efficiency when we're looking for values within these trees. So here we're just recapping some material that was already covered in the first lecture of this chapter. And there we saw that in a perfect world, if we have a nicely structured tree, then each iteration in our search to find a particular value in the tree will eliminate half of the search space. So what this then means is that if we have n nodes within our tree, then the number of steps is defined by how many times we can divide the full search space defined by all of the values in the tree by 2. So the answer to this then is that we simply compute the log base 2 of n and compute the floor of that, and that will then give us the number of times that we can divide our search space by 2. So essentially this will then be the number of comparisons that we perform, and therefore the complexity of this well-structured tree is O log base 2 of n. However, it's not guaranteed that our trees will be nicely structured. So in an imperfect world, we may have a situation such as this. So over here we can see that we have a tree structure in which each node only has a single child. And this is the worst case possible scenario for a binary search tree. The reason for this is that we've actually essentially just got a regular linked list here, even though it is a tree that we're representing, because each node is connected to only one other node as a child. This means we're basically working with a linear data structure. And of course, we know then that the complexity for searching a linked list of values one connected to the other is then simply ON. So this is of course then not great performance, and what this then implies is that we can maintain the efficiency of our trees if we can get them into a position that is nicely structured, such as this, rather than a situation where we have a poorly structured tree, such as the second example. Now, it turns out that this kind of well-structured tree is referred to as a balanced tree, and we'll be defining exactly what we mean by this in the next few slides. So before we can get on to the actual definition of a balanced tree, we need to ask the question, what makes a tree efficient in terms of searching the tree? Well, as we've previously mentioned, what we essentially want to be able to do during search is eliminate approximately half of the search space each time that we follow a branch in the tree. So what this implies then is that the height of the left and right branches of every node within the tree should be more or less the same height, and this will then ensure that approximately half of the search space is eliminated at each search step. So we will then specify this condition as allowing a maximum difference between the height of the right and left branches of any particular node of 1. So let's look at this in terms of these three trees over here. Let's look at the left tree first, and we need to then consider every node within this tree. So let's look at the root node over here. If we look at the left tree, we see that we have a tree of height 2. and on the right branch we have a tree of height 3. So the difference then between those two heights is of course 1, which means that the condition is satisfied for the root node. If we look at the node containing the value 1 over here, we have a right subtree that has a height of 1 and a left subtree that has a height of 0 because there are no nodes to the left of the node containing the value 1. So once again, we have a difference of height that is equal to 1 in that case. If we consider the node containing the value 7, then we see that we have a left tree which has a height of 2 and a right tree that has a height of 1. So again there the difference is 1. And then if we consider the node containing the value 6, we see that we have a left subtree that has a height of 1. There is no right subtree, so that height is implicitly 0, which once again means there is a difference in height between the branches of 1. So because this condition then holds for every node within the tree, this will then be a fairly efficient tree for us to search. If we look at this middle tree over here, we can see the same situation is true here as well. So for example, with the root node, we then have a right subtree that has a height of 2 and a left subtree that has a height of 2. The difference between those heights is of course 0, and that is less than the maximum difference of 1. We can also see for this node 3, we have a difference in the left and right branch heights of 1. For the node 7, we have a difference in the height of the left and right branches of 0 once again. So in this case then, we have a very well balanced tree. It is a tree that will eliminate approximately half of the search space at each step. However, if we look at this tree on the right over here, we can immediately see that we don't have a very efficient tree structure. So all we need to do is look at the root node. We see that the height of the right branch is then 4 in this case. The height of the left branch is 0 because there are no nodes to the left, and so we have a difference of 4 between the left and right branches, meaning that we don't have an efficient tree structure. So now we are ready to move on to the concept of a balanced binary tree and define what this actually means. Now, there are different levels of balancing that are possible. So the first basic kind of balancing is if a binary search tree is height balanced. So a binary search tree is height balanced if the difference in height of both subtrees of all nodes is either 0 or 1. And this is essentially what we defined on the previous slide. So what we can see here then is that this tree on the left is height balanced. If we look at the heights of the left and right subtrees on each branch for every node, we will see that the difference is at maximum 1. If we look at this tree here in the middle, we see that it is also height balanced. If you consider each individual node within the tree, you will also then see that the left and right branches differ in height by a maximum of 1. Of course, as we saw in the previous slide, this right tree over here is not height balanced, and this is because the difference between the height of the root node, for example, is greater than 1, and this means that we then don't have a height balanced tree in this case. Now, we also then have the concept of a perfectly balanced tree, and this will become important later on in this lecture. And a perfectly balanced binary search tree is a tree that is height balanced, but also then additionally all of the leaves are on 1 or a maximum of 2 levels. So we of course don't need to consider the rightmost tree because that isn't height balanced at all. If we look at this left tree over here, we see that all of the leaf nodes occur on the same level of the tree. So this means that we have a perfectly balanced tree on the left here. If we look at the middle tree, we saw that it was height balanced, but we can see then if we look at the leaf nodes that we have a leaf node over here, we have 3 leaf nodes on that level, and we have a leaf node on that level as well there. So what we see then is that we have leaf nodes that are split across 3 levels, and this means we then don't have a perfectly balanced tree, but we do have a height balanced binary search tree. So the question that now arises is, how do we get a balanced tree? So the order of insertion of values into a binary search tree matters. So let's assume that we are inserting these characters in this order. So we have A followed by D, followed by E, followed by F, and then finally Z. So let's look at how this insertion would work in our binary tree structure. First of all, we insert A, so A of course becomes then the root of our tree. Then we insert D. D is alphabetically after A, so that will then be inserted as the right child of the root node. Then we insert E, so E becomes then the right child of node D because it is alphabetically after both A and D. Next we insert F, so F is alphabetically after A, D and E, so again it will then be inserted as the right child, this time of node E. And then finally we insert Z, and Z is alphabetically after A, D, E and F, so therefore it will be inserted as the right child of node F. So what we see then is that this order of insertion has created a completely unbalanced tree. Now let's assume that we are inserting the same set of characters, but we're inserting them now in a different order. So we are first inserting E, then A, then D, then F, and finally Z. So let's look at the tree structure that is generated by these insertions. E is the first character that's inserted, so of course it is then the root node. Then we insert A. Well, we see that A is alphabetically before E, so it is then inserted as the left child of the root node. Next we insert D, so we see that D is alphabetically before E, but alphabetically after A, so therefore it's inserted as the right child of node A. Next we insert F, so we see that F is of course alphabetically after E, meaning that this character is then inserted as the right child of the root node. And then finally we have Z. Well, Z is alphabetically after both E and F, so it is then inserted as the right child of node F. So what we've seen is that simply by altering the order that we insert characters, we can produce then a perfectly balanced tree as we see on the left over here. So this brings us then to the simplest approach we can use to generate a balanced binary search tree. In order to do this, we need all of the data that is going to be inserted into the tree, and we need to sort this data in ascending order. Then we need to find the middle value in the sorted list of our data, and then we insert that middle value. So if we look at our previous example over here, if we were to order these values in alphabetical order ranging from A up to Z, then we would see that the middle value would be E, and we insert that then as the root node in our tree. So now we've basically divided our list in half, and then all we need to do is recursively perform the same operation on the left half and the right half. So because we've inserted E, we then have our initial list which contains A and D, and then we have a second list containing F and Z. Once again, we then need to find the middle value of those lists, and then we perform an insertion. So this will essentially then guarantee that we have a balanced binary search tree. Now, are there any problems then with this approach? So what I would like you to do at this point is pause the video and try to think of one or more drawbacks to this kind of approach for balancing. Right, so the first and most obvious drawback is that we need an external data structure. This is in order to store the data that we are working with. So we need to have some kind of array or linked list type structure that sequentially will store all of this data we are inserting. Also, we need to perform a sorting operation, and sorting is a fairly computationally expensive operation, even in the best case scenario. So this will obviously then increase the time complexity of this balancing approach. And then finally, a question that I'll pose to you again, must we do this every time an item is inserted? So pause the video and try to answer this question. So the answer is that it depends on what kind of insertion happens. If an insertion creates a balanced tree, or rather maintains a balanced tree, then we don't need to do anything further. So for example, if we were to insert a node to the left of node F, then we would still have a balanced tree structure. However, if we perform an insertion that unbalances the tree, so for example, perhaps we insert a node to the right of node D, then that will unbalance the tree, and then essentially we have to perform the whole operation again. So this means then taking all of the data that's already contained in the tree, sorting it again, and then performing a series of insertions. And obviously, if we're inserting data fairly rapidly, this means we're going to waste a lot of time reconstructing trees over and over again. So this approach does work, but it's not a very efficient approach in practice. So this brings us to our first proper widely used algorithm for balancing binary search trees. And this algorithm is called the DSW algorithm. The D, S, and W relate to the first letter of the names of the developers of this algorithm, Day, Start, and Warren. So the DSW algorithm is then a method that we can use to efficiently balance binary search trees, but very importantly without the need of any additional data structure. So we don't require something like a list or an array to contain all of the values that will be inserted into the tree. So what the DSW algorithm does is it starts with an arbitrary binary search tree. This tree does not have to be balanced, it can be completely unbalanced, and then it converts this tree into a perfectly balanced binary search tree. Now, how it achieves this is by means of a series of what are called tree rotations. So before we can discuss the DSW algorithm itself in any kind of detail, we first need to look at what a tree rotation is and how we perform such a rotation. A single tree rotation swaps the roles of a child node and parent node, but very importantly, it does this without breaking the binary search tree relationship. So in other words, after a rotation, we will still have a situation where all of the values stored in the right branch of a node will be values that are larger than the value that that node contains, and all values to the left of that node will be values that are smaller than the value that that node contains. So there are two types of rotations. Firstly, we have a left rotation, and in this case, the parent node becomes the left child of its right child. So what this means in practice is that the parent moves to the left. So let's assume that we have this simple tree over here. We can see that the binary search tree relationship is maintained there. A is to the left of D and E is to the right of D. So if we perform a left rotation, what this means then is the parent, in other words D, becomes the left child of its right child, which in this case is node E over here. So what we then have is a situation where we have node E, the previous parent, node D, has become its left child, and then node A remains the left child of node D, as was the case originally. So what we would say then in this case, in terms of the terminology that we would use, is that we've performed a left rotation of child E about parent D. So the second kind of rotation that we can perform, as you've probably guessed, is a right rotation, and this is essentially the opposite operation to a left rotation. So in this case, the parent becomes the right child of its left child. So in other words, the parent then moves to the right. So again, if we start with our original tree over here, then this parent D becomes the right child of its left child A. So we can see we have a situation here where A has a right child, which is D, and that was originally the parent node, and then node E, which is the right child of D, has not changed position because it was the right child of D to begin with. So the previous slide covered relatively simple situations where we perform left and right rotations. However, what happens if the child nodes that are rotated are not leaf nodes? So let's look at this example over here, and we will assume that we are performing a right rotation of C about the parent G. So according to our previous definition, G then needs to become the right child of its left node. So in other words, it needs to become the right child of node C. However, node C already has a right child, which is node D. So we need to somehow then deal with node D and also still maintain the binary search tree property. So let's look first of all at the right rotation algorithm. And the first step is exactly as we saw on the previous slide. So the parent becomes the right child of its left child. In other words, G then becomes the right child of C. But now we need to deal with D. So the left child's right branch, which will then be just the node D over here, but if there are children under D, it would also include those, then become the old parent's left branch. So they become the left branch of G. Because we've rotated G, this means that the left branch will then be open, and then D can move into that position. So if we look at this in terms of our binary search tree property that needs to be maintained, we have C, D, and G. So D can then either be right of C, as it is in this case over here, but it can also be left of G because it is alphabetically before G. Alright, so let's look at how this would then work in practice. So we are performing a right rotation. This means that G then becomes the right child of its left child, which is C. So you can see that that's exactly what's happened there. B, H, and J don't change structure at all, so H and J are still, after the rotation, right children of G, and B is still the left child of C over there. So this then just means we need to deal with node D, so this will then become the left child of the old parent. So G has now rotated down, and D then becomes its left child, as you can see over there. So we've looked at how a right rotation works in terms of how it moves nodes around. So let's now look at how we would practically implement this kind of rotation in terms of the references between nodes in the tree. So here we have three nodes, G, P, and C over there. Now it's important to note that those letters don't represent values within the tree. C simply denotes the child, which will be rotated around the parent, which is P, and then we have a grandparent G of node C in this case, which is the child. Right, so while we perform this rotation, it's very important that we don't lose references to parts of the tree. So we need to always make sure that there is a reference to a node that is being moved during the rotation process. So our first step then is that our grandparent node G, which is the grandparent of child C, then needs to become C's parent. And this is because C will be moving up and to the right, and the parent node P will be moving down and to the right. So essentially what we then do is we sever the link between G and P, and we create a link between G and C in this case. So notice that we haven't lost any reference then to this portion of the tree over here. We still have our grandparent referring to it. So now the next step is that the right subtree of C becomes the left subtree of C's parent P. So we can see that C's parent P has a left connection to node C. We now need to make sure that the left branch pointer for P now refers to the right subtree of node C. In other words, what is indicated as Y in this diagram. So that means then that we sever the connection between P and C, and we then create a connection along the left branch connecting P and subtree Y over here. Notice that we haven't lost a reference to C because it is still referred to via the grandparent's right branch. So next, node C then acquires P as its right child, and this is then the final step that we perform. So we can see then that node C in this case has a right child which is subtree Y. So we then sever that connection, and we now make C's right child P, which is its former parent, and this then creates a situation where P has now rotated down and C has become its parent. Now that we've looked at right rotations, we can consider left rotations. And a left rotation is simply the opposite of a right rotation, which we've already discussed. So we saw that with a right rotation, the parent becomes the right child of its left child. In the case of a left rotation, the parent becomes the left child of its right child instead. And then as the second step for a right rotation, the left child's right branch becomes the parent's left branch. In the case of a left rotation, the right child's left branch becomes the parent's right branch. Let's now look at how we would perform a left rotation in terms of practical examples. So over here we have a similar diagram to what we saw before. We again have three nodes. So we have node C, which is the child, node P, which is the parent, and node G, which is the grandparent. What we now want to do is rotate the child node C about the parent node P, and this of course then must be a left rotation. So what we then need to do is rotate C up. P must become then the left child of C, which we can see over here. So P is now the left child of C. However, C already has a left subtree, which is Y, so this must now become the right subtree of the parent P, as we can see over here. So let's look at this in terms of an actual binary search tree. Here we have a series of letter values stored within a binary search tree, and we then want to perform a left rotation around C. So in other words, G is going to rotate about its parent C. So take a moment to pause the video and try to draw the tree that would result from this left rotation. So this is then the result that would be produced. So G then rotates upwards. It becomes then the new root node, as you can see there. Its parent then becomes the left child of G. So C then, as we can see here, is the left child of G, but because G then also has a left node D in this case, we need to reposition this left node as the right child of C, and that's exactly what we have done over here. Now that we've discussed tree rotations, we can move on to the DSW algorithm itself. So the basic idea behind the algorithm is a two-step process. The first step involves linearizing the tree into a single right branch, which we usually refer to as a backbone. So this essentially constructs a tree where we have a single root node, of course, but then every other node in the tree is a right child, and none of the nodes have left children. Then, once we have performed this linearization process in order to construct a backbone, then we perform a series of left rotations on this linearized tree, and this will then eventually construct a perfectly balanced tree. So let's first of all look at the process that we need to go through in order to create a backbone. And this is then a pseudocode representation of the algorithm that we will use. So we need then a temp, which is essentially a pointer or a reference that can refer to a node in the tree, and temp initially refers to the root node of the tree that we want to balance. So then we have a loop that continues, and inside the loop we then check temp, and we test to see whether it has a left child or not. So if temp then has a left child, then we perform a right rotation of this child about temp. So in other words, temp will then rotate down in the tree, and the left child will rotate up to become temp's parent. Then we set temp to the child which just became the parent. So in other words, the node that has just rotated up by means of the right rotation. Now, if temp does not have a left child, then no rotation needs to be performed, and in fact, no right rotation can be performed in that case. So then we simply set temp to the node's right child. So this continues then until eventually temp becomes null, and this will then be a situation where we eventually get to the last node of the linearized tree. We then attempt to set temp to its right child, but there is no further right child, and that will then terminate the backbone creation process. The algorithm for creating a backbone that we discussed on the previous slide may be a bit difficult to visualize in terms of what it actually does. So let's illustrate the operation of this algorithm by means of a practical example. So over here we have a tree, and we want to create a backbone including all of the nodes that are contained within this tree. So to begin with, we then have our temp pointer, and that refers to the root node of the tree. In other words, the node containing the value 10. So now we need to perform a test to see whether there is a left child of the node that temp currently refers to. Well, of course, there is a left child, namely 5. So what this means is we need to perform a right rotation, and we are rotating 5 about its parent, which is the node containing the value 10. So this is the result then of the rotation. We can see that 5 is moved up to become the new root node. 10 has become the right child of the node containing the value 5, and then we set temp to refer to the node that has just been rotated up to become the new parent. So seeing as 5 has rotated up to become the new parent, temp now refers to that node. So now we need to again check the node referred to by temp and see whether it has a left child. Well, of course, there's no left child for node 5, so this means we then just simply traverse down to its right child, which is node 10. Again, we check node 10 to see if it has a left child, and once again we see it doesn't, so we traverse again to the right. At node 15, we perform the same check, see again that there is no left child, so we then move down to node 20. So then we again perform this check, and we see that node 20 does have a left child, which is node 16 in this case. So this means we then need to perform a right rotation of the left child, 16, about its parent, 20, over here. So this is the result of that rotation. We can see then that 16 has rotated up into the parent position. The old parent, which was 20, becomes the right child of the node that has rotated up. But then we see also that the node that has rotated up previously had a right branch containing the nodes 17 and 18, so these now need to become the left child of the old parent node that has been rotated down, in other words, node 20 in this case. Again, we then set our temp pointer or reference to refer to the node that has just been rotated up. So this is node 16, and as you can see here, temp now refers to 16. So again, we then need to perform the same test for a left child on node 16. We see that there's no left child, so we then traverse down to node 20. Again, we perform the same test, and we see that node 20 has a left child, namely node 17. So what this means is, once again, we need to perform a rotation, and this rotation will then rotate node 17 about its parent, which is node 20. So if we perform this right rotation, we then end up with the following tree. So we see that 17 has rotated up to become the new parent. We see that the old parent, which is node 20, has rotated down to become the right child of node 17. However, we have to also then deal with the right subtree of node 17, which is just node 18, and so this becomes the left child of the old parent, which is node 20 in that case. Again, we then have temp referring to the left child that is just rotated up, so we rotated 17 up into the old position of node 20, so therefore we have temp referring to node 17. So again, we need to perform a check to see whether node 17 has a left child. It of course doesn't, so we then just traverse to the right. And now we see that we again have a node with a left child. In this case, it's node 18 that is the left child. So again, this means that we need to perform a rotation, and we need to rotate node 18 about its parent, which is node 20 in this case. So this is then a simple rotation. We just rotate 18 up to become the new parent. The old parent, which is 20, becomes the right child of the left child that has just been rotated up. And then, of course, we have the node 30, which is still the right child of node 20. Again, we have temp then referring to the child that has been rotated up into a parent position. So because we rotated 18 up into the position that 20 occupied, we now have temp referring to node 18. So again, we then need to test node 18. We see that there's no left child, so we traverse to the right. We see that node 20 also doesn't have a left child, so again we traverse to the right. And at this point we then check to see whether node 30 has a left child. Again, it doesn't, so temp then gets updated to 30's right child, which is of course null, and that then terminates our loop. So we can see now that we've constructed a full backbone. Every node other than the root is a right child, and there are no left children at all within this tree. And we can also see that this tree maintains the binary search tree structure. So we haven't disrupted the structure or order of the nodes at all. We still have a binary search tree. Now that we have a backbone, we need to convert this backbone into a perfectly balanced tree. So in order to do this, we need to look at the properties of a perfectly balanced tree. And what we saw previously is that a perfectly balanced tree is height balanced, but it also has leaf nodes on a maximum of 2 levels. So in order to do this, we will be performing a series of left rotations, and we need to work out how many left rotations are required. So the number of left rotations that are performed are based on the number of nodes contained in the backbone, in other words, the number of nodes in the entire tree, and also the number of nodes making up a full tree of the required size. And then possibly some additional overflow nodes, which will then be leaf nodes on the next level of the tree. Let's now compute some of the values that we require in order to calculate how many left rotations need to be performed on the backbone. So we start off with the backbone, and the first value that we have is n, which is the number of nodes in the backbone. So this is simply equivalent to the total number of nodes in the tree. So now we need to ask the question, how many levels will a resulting perfectly balanced tree have given this value of n? So let's look at a perfectly balanced tree of height 3 over here, and we can see that we have a varying number of nodes at each level. We can see that at the root level we have 1 node, which is 2 to the power of 0. On the second level we have 2 nodes, which is computed as 2 to the power of 1. And on the third level we have 4 nodes, which is computed as 2 to the power of 2. So essentially we can compute the number of nodes at each level by taking 2 to the power of 1 less than the level that we are at. Right, so we can see then in this tree that our tree height, h, will be the symbol that we'll use to denote the tree height, and this has a value of 3. So how many nodes then do we have within this tree? Well, we can simply count them, and we see that we have 7 nodes. Now this can be expressed by means of the following computation. So we have 2 to the power of 3, 3 being the height of the tree, and then we subtract 1 from that. So we can see that this formula also holds for a smaller tree. So let's assume that we're just looking at the tree within the triangle. Here then h would have a value of 2 because we have 2 levels within this tree. So the number of nodes would then be computed as 2 to the power of 2, which is 4. And if we subtract 1 from that, we have 3, which is then the number of nodes within this triangle. Alright, so what we have now computed is the number of nodes n given the height of the tree h. But what we really want is to calculate the height of the tree h, in other words, the number of levels in the tree given a particular number of nodes which we know up front because we know how many nodes are in the backbone. Alright, so let's then write down this formula that we have been using so far. So we have n, which is the number of nodes in the tree, and this is then equal to 2 to the power of h, where h is the height of the tree, and then we subtract 1 from that. So let's then rewrite this by moving the 1 from the right-hand side to the left-hand side. So then we have 2 to the power of h, which is equal to n plus 1. We can then just take the log of base with base 2 of both sides. So this gives us then h on the left-hand side and log base 2 of n plus 1 on the right-hand side. So this is now the equation that will give us the height of a perfectly filled tree given n nodes. Now, of course, this assumes that the n value that we have actually fills then a perfect tree. So in other words, we have sufficient nodes within our backbone that can create a perfect tree that is perfectly full, as you can see in the example over here. So what happens then if we have an n value that doesn't perfectly fill a tree? Well, we can just increase n by 1 in this example, so we're increasing it from 7 to 8, and that node will then have to be placed on the next level because all of the previous levels are completely full. So we can then basically perform a computation. Here we have our computation that calculates the height of our tree given n. Now we take the floor of this height because we are also trying to deal with situations where we have nodes that can't completely fill a perfect tree. So for example, in this case where we have an n of 8, we would then be computing the log with base 2 of 8 plus 1, in other words 9. Now the result of that will be 3 with a fractional portion because the height of the tree is 3 with some extra height added for this additional node here, but it will be a fractional portion because this fourth level is not completely full at this point. So that's why we take the floor of that computation, and then we can take 2 to the power of that height minus 1, and this will then give us m, and then in this case m is the number of nodes in the largest full tree to be made out of n nodes. So if we have an n of 8, as in this example, then we will compute this log over here, which will then give us a height of 3. So that is then the height of the largest full tree that we can construct given n, and then we compute the number of nodes within that using this equation over here, and that will then give us the number of nodes within the largest full tree. Now we can move on to calculating how many left rotations are required in order to create a perfectly balanced tree. So as I've previously mentioned, we already know how many nodes there are in the backbone, the total number of nodes in the tree, and that we refer to as n. We then calculate our m value as we did on the previous slide, and this then represents the number of nodes in the largest full tree that we can construct given n. So the largest full tree will then be the largest tree in which every level is completely occupied by nodes. Now we calculate the difference between these values, so we take n and we subtract m from that, and this will give us then the number of overflow nodes that need to be in the tree beyond the largest possible full binary search tree. So if we look at our previous example where we had 8 nodes within our tree, then m will give us a value of 7. That's the number of nodes in the largest complete tree. So then we take m, which is 8, subtract 7 from that, and that gives us 1. And as we saw on the previous slide, there's one additional node then on the lowest level that couldn't be fitted into the largest full tree. So this difference then will tell us how many overflow nodes there are, and these nodes will then be rotated such that they are the leftmost leaves in the resulting perfectly balanced tree. Now, what's important to note here is that whenever we perform a left rotation, we rotate every second node in the backbone, and we'll illustrate how this is done in an example that we'll work through in a moment. So we then need to perform 2 steps. The first step deals with the overflow nodes that we have within our tree. So we rotate then the backbone left n minus m times. In other words, we perform a left rotation for each one of the overflow nodes. But very importantly, note that it is every second node in the backbone that we will rotate. So once we've completed step 1, we've dealt with all of our overflow nodes, and now we need to construct our full binary search tree, which is the largest possible full binary search tree we can create given our particular value of n that we're dealing with here. So what we then do is we iterate over m, and we continue doing this while m is greater than 1. And at each iteration, we then divide m by 2, and this will then give us a new m value and tell us how many rotations are required within the tree as left rotations. So we will perform then a series of multiple left rotations at each step until eventually m is not greater than 1. So here we have the procedure represented in pseudocode. Our algorithm is called create balanced tree, and we are of course assuming that we have created a backbone prior to this. So we then need the value n, which is the number of nodes in the backbone. We have to compute m, which is of course the number of nodes in the largest full binary search tree that we can construct given our n value. So then we compute the difference between these values. So we compute n minus m. This gives us the number of overflow nodes, and we perform that many left rotations starting with the top of the backbone and rotating every second node. So once we've completed that set of left rotations, we've dealt with the overflow nodes. Now we get into this loop over here, which continues while m is greater than 1. We update m's value by dividing m's old value by 2, and that then gives us the number of left rotations that we need to perform starting at the top of the backbone in order to deal with the current value of m. So what we see then is that m's value decreases at each step by half, and this means we will be performing fewer and fewer left rotations for each iteration. And this while loop will then construct the full binary search tree, which can be constructed given our particular value of n. So let's now apply this algorithm that computes how many left rotations are required at each step. And let's do this with the tree that we previously discussed in our earlier example. So we saw that that tree contained 8 nodes, therefore n has a value of 8. We can then also compute the floor of the log with base 2 of n plus 1, which will give us a value of 3, and this is the number of levels in the largest perfect tree that we can construct given 8 nodes. So now we need to compute the number of nodes in this largest perfect tree, which has 3 levels, as we've just indicated. So we compute then the value of m by taking 2 to the power of 3, which is the number of levels, and then subtracting 1 from that, which gives us a value of 7. So this then indicates the number of nodes in the largest full tree that we can construct given 8 nodes. So now we need to determine how many overflow nodes there are. We do that by taking n and subtracting m from it. So that is then 8 minus 7, which gives us a value of 1. So this indicates we have a single overflow node to deal with, and therefore we perform 1 left rotation. Now we need to deal with the iterations of our while loop based on m's value. So to begin with, m has a value of 7 as we've computed up here. So we then divide 7 by 2, and this gives us a value of 3. We're rounding down, of course, on any fractional portions of this division. So that then gives us a set of 3 left rotations that need to be performed. Then we take m's new value, which we've computed as 3. We divide that by 2, which gives us a result of 1, which means we then subsequently perform a single left rotation in addition to the previous 3 left rotations. It's important to understand that each of these sets of rotations start at the root of the tree, and we rotate every second node. So our first 3 rotations we perform starting at the root, and then our single rotation here again begins then at the root. So this will then construct our perfectly full binary search tree out of our n nodes, and because we've performed this initial rotation, which is a single rotation, that will then also ensure that our single overflow node appears on the far left of our tree. Now let's look at how these left rotations will actually affect the tree, assuming the calculations that we performed on the previous slide. So we are going to assume that we have the backbone that we constructed previously by means of a series of right rotations, and then we saw that we need to initially perform a single left rotation, and that is to deal with the single overflow node within the tree. So again, remember that we rotate every second node in the tree. So we are rotating 10, which is the second node in the tree, left about its parent, which is the root node in the tree. So the result of this then is that 10 becomes the new root of our tree, and the old root, which was 5, is rotated to the left of it. So this then deals with our single overflow node. What we now need to do is perform the rotations that are computed in our while loop. So we saw on the first iteration of our while loop that we need to perform 3 rotations. So what this means then is we are again starting at the root of our tree and rotating every second node. So we rotate then 15 about 10, we rotate 17 about 16, and then we finally rotate 20 about 18. So you can work out these rotations. For brevity's sake, I'm not going to go through every step showing each of the rotations, but this is the tree that we then produce by means of these 3 left rotations. We can see also importantly that we still have this node 5 over here, which is our overflow node. So now we move to the second iteration of our while loop, where we determined that we need to perform a single left rotation. And again, we start then at the root of our tree and we rotate every second node. So we're only performing 1 left rotation, meaning that we take our second node to the right over here, which is 17, and we rotate that about the root node, which is 15. So the result of that rotation is then this tree over here. We can see that we have completely filled up the largest possible binary search tree that is full. In other words, every level is completely filled with nodes, and then we have our single overflow node all the way to the left here, which is the node 5. So we've now seen that the DSW algorithm is a good approach for creating a perfectly balanced tree from an unbalanced tree. Now what I would like you to do at this point is again pause the video and try to think of a disadvantage associated with the DSW algorithm. Alright, so the major disadvantage with the DSW algorithm relates to what happens when we insert or delete a node within the tree. So what we see then is that the DSW algorithm works on the global tree structure. In other words, it balances the entire tree as a single entity. So what this means is when we insert a node or delete a node, then the entire tree needs to be rebalanced again, which means we need to re-execute the DSW algorithm again on the tree, which means we once again have to create a linearized backbone, and then we again need to perform left rotations in order to create a perfectly balanced tree. So what we really want to make this balancing procedure more efficient is an algorithm that will adjust the tree structure locally. In other words, only at the point where an insertion or a deletion unbalances the tree. And this will only occur when an item is added to the tree or removed from the tree, and we will perform these adjustments in order to maintain the balance of the tree. So AVL trees were invented back in 1962 by 2 Soviet scientists, and again the name of the algorithm comes from the last names of the inventors, Adelson, Velsky, and Landis. So in an AVL tree, the subtrees of every node differ in height by at most 1. So what this means is we are not dealing with perfectly balanced trees, we are dealing with only height balanced trees. And then also every subtree within an AVL tree is also an AVL tree. So let's look at 3 examples of trees over here. If we look at the leftmost tree and we consider initially the root node, then we see that there is a difference in height between the 2 branches of 0 because the right branch and the left branch both have a height of 2. We can also see that for both A and F, we have a height difference of 1, and this is because each of those nodes has a single right child and no left child, meaning that there's a difference in height of 1. So this will then be a valid AVL tree. If we look at this middle tree over here, and we consider initially the root node G, we see that there is a difference in height of 1 because the left subtree has a height of 2 and the right subtree has a height of 1. Obviously, with node H, we are dealing with no children, so that also satisfies the AVL tree requirement. And then if we look at node C, we have a height difference between its left and right subtrees of 0 because the heights of those subtrees are both 1. So again, then this middle tree is an example of an AVL tree. If we look at our last tree over here on the right, we see with our root node over here that we have a difference in height between the left and right subtrees of 1. This is because the right subtree has a height of 3 and the left subtree has a height of 2. So there the difference is 1. If we look at node 1 over here, we see again that we have a difference of 1 because the right subtree has a height of 1 and the left subtree doesn't exist, so it has a height of 0. If we look at node 7 over here, we see again we have a height difference of 1 because we have a left subtree that has a height of 2 and a right subtree that has a height of 1. And then finally, if we look at node 6 over here, we again have a height difference of 1. This is because the left subtree has a height of 1 and there is no right subtree, so that is a height of 0. On the previous slide, we introduced these two properties which an AVL tree must have. So what this means is when an item is inserted into the tree or deleted from the tree, then these two properties must be preserved. So how do we then achieve this? Well, every node within our AVL tree stores an additional piece of information which we call a balance factor. And this is simply a number that indicates the difference between the height of the right and the left branch of that particular node. So in other words, the balance factor then is the height of the right subtree for our node, and then we subtract from that the height of the left subtree. So what this then means is in a valid AVL tree, every node must have a balance factor of either -1, 0, or +1. Any balance factor that is larger in the negative or positive direction will then indicate an unbalanced tree. So let's look at what these balance factors then would look like in some real trees. Over here we have a simple tree. We have a single leaf node over here. Its balance factor is of course 0 because it has no nodes to the left or right of it. We then have our root node over here, so its balance factor then indicates the height of the right subtree, which is 0, and then subtracted from that the height of the left subtree, which is 1, so this gives us a balance factor of -1. If we look at our middle tree over here, we can again see that each of the two leaf nodes have a balance factor of 0. This node has a balance factor of -1 because again we're taking the height of the right subtree, which is 0, and subtracting it from the height of the left subtree, which is 1, and this gives us a result of -1. Our root node here has a balance factor of 1, and this is because our right subtree has a height of 2, whereas our left subtree has a height of 1, and if we perform that subtraction we get a result of +1. We also have the same kind of structure in the rightmost tree over here. I'm not going to work through every node, but as you can see, the balance factors for each node are either 0, -1, or +1, indicating that we are working with an AVL tree once again. So then when an item is inserted or deleted, then the balance factors are updated within the tree to accurately reflect the addition of this new item. And if the balance then is lost, which will be detected by the balance factor of a node becoming -2 or +2, then the tree needs to be rebalanced. We therefore need to discuss insertion and deletion of nodes within AVL trees. We'll start first of all with insertions of new values into an AVL tree. So the question we need to ask then is, how can an AVL tree get out of balance? So let's consider a simple case, first of all, where we have a tree where the left and right branches are of the same height, and we perform an insertion into this tree. So here we have a simple example of such a tree. We have our root node G, and we can see that the left and right branches have exactly the same height. So what this means then is that the balance factor of G will of course be 0. So what I would like you to do at this point is pause the video and try to answer whether this tree can become unbalanced due to an insertion. So of course the answer to this question is no, because any insertion that we will perform will either fall under node C or under node H. Either way, we still have a difference of 1 or -1, depending on which side we have inserted the new node into, and therefore we still have a balanced AVL tree. So now let's consider a case where we have a tree where the left branch is longer than the right branch. So here we have an example of such a tree. We can see that the left branch has a height of 2 and the right branch has a height of 1. So this is a balanced AVL tree, but now the question is, if we perform an insertion, can this tree then get out of balance? So pause the video again and try to answer this question. So the answer then depends on where the insertion occurs. If we perform an insertion that falls under node H over here, we still have a balanced AVL tree. However, if we perform an insertion into the left subtree of node G, then we have an unbalanced AVL tree that will be created. This is because the insertion must occur either under node B or node D, but either way we have then increased the height of the left subtree to 3, the height of the right subtree is 1, so we have then a situation where we have 1 minus 3, which gives us a value of -2 as the balance factor for node G, indicating that the tree is now out of balance. So what about if the right branch is longer than the left branch? Well, this is essentially the mirror image of our previous case. So over here we have a right branch that is longer, in other words, has more levels than our left branch over here. So, of course, if we insert a node under node C, then we don't have a problem because the AVL tree is still balanced. But if we insert into the right subtree, in other words, under node H or node J, then we have an unbalanced subtree. The result of that insertion will be that the height of the right subtree of G will become 3. The height of the left subtree is still 1, so then we have 3 minus 1, which gives us a balance factor of 2 for our root node G in this case. That then indicates that our AVL tree is out of balance. Start then by considering the simplest kind of insertion and how this affects our balance factors. So we'll assume at this point that we are performing an insertion into an AVL tree, but it doesn't unbalance the tree. So what this means then is, of course, that no rebalancing is necessary. and all we need to do then is update the balance factors for the nodes in the tree, and we do that by moving back from the inserted node towards the root of the AVL tree. Now, how we update the balance factor depends on which branch the insertion has occurred in for the node that we are currently considering. So if we insert in the right branch, this means we need to increase the node's balance factor by 1, and if we insert into the left branch, then we decrease the balance factor by 1. The reason for this is if we're inserting into the right branch, we are then making the right subtree one level deeper, which means then that we will have a difference of 1 more between the right subtree that is increased by level and the left subtree which is not increased. The opposite is true if we insert in the left branch of a node, because what then happens is the left branch has increased in height by 1, the right branch has remained unchanged, and therefore we have a more negative difference that occurs. Alright, so let's assume then that we have this AVL tree over here. We have each node annotated with its respective balance factor, and if you check those balance factors, you will see that they are all correct. So now we assume that we are inserting one additional node, and this is just a regular insertion as we would do with any binary tree, and this then results in I being inserted at this point as the right child of node H. Now, of course, the new node that has been inserted is a leaf node, so this means that its balance factor must be 0 because it has no right or left children. We then move up to its parent node, and because we saw that the insertion occurred on the right branch of this node, we then need to increase the value of the H node's balance factor by 1. So we saw that the balance factor was 0 to begin with because H was a leaf node, so therefore we need to increase this value by 1, giving us a positive 1 balance factor for node H. We then move on to the parent of H, which is the root node G at this point. We saw then that the insertion occurred under node H, so this is then under the right branch of node G, and so once again we need to increase node G's balance factor by 1. So we saw that its original balance factor was -1. If we add 1 to that, we of course get 0, and that is then the new balance factor for node G. Now notice that none of the balance factors have become -2 or +2, so this means we are still dealing with a balanced AVL tree. And also note that none of the balance factors for nodes C, B, and D have changed between the initial state and the updated state that has occurred due to the insertion. So we can already see here then that the updates are only localized updates. They only apply to the nodes that are affected by the insertion. So on the previous slide, we discussed the case where an insertion doesn't unbalance the tree. However, an insertion may unbalance the tree. So what we need to do then in this case is update the balance factors once again for the nodes from the new node that has been inserted, moving back from the inserted node towards the root of the AVL tree, but we also then need to rebalance the tree. Let's now analyze the different situations in which an insertion into an AVL tree can unbalance the tree. So it turns out we have 4 such cases. This is the first case where we are inserting node A into our AVL tree. So as we've previously mentioned, we need to update the balance factors from the newly inserted node all the way up to the root. So we will update the balance factors for nodes B, C, and G. Now we will see that the balance factors for nodes B and C will still be valid as far as the requirement for an AVL tree is, but as soon as we get to node G over here, we will see that the balance factor is updated to -2. This is because the right subtree has a height of 1 and the left subtree now has a height of 3. So we then take 1, subtract 3 from that, and that gives us a balance factor of -2. So what's important to note here is that the insertion is occurring under the left child of the node that has become unbalanced, and it is occurring in the left subtree of that node. The second case is illustrated over here. So here we are inserting node E. Again, we'll update the balance factors all the way up to the root. So we update the balance factors for nodes D, C, and G. We will again see that the balance factors for nodes D and C will still be valid. However, when we update the balance factor for node G, we will see then that we will get an invalid balance factor. This is because we have a right subtree of height 1 and a left subtree of height 3. So 1 minus 3 will give us once again a balance factor of -2, which is invalid and then needs to be rebalanced. Our third case then deals with an insertion under the right child of the root. So here we are inserting node D in this case. Again, we update the balance factors all the way to the root, so that will be for nodes H, I, and C. Again, the balance factors for H and I will still be valid. However, when we update the balance factor for node C, we will see that we get an invalid balance factor. This is because the right subtree now has a height of 3, and we subtract from that the height of the left subtree, which is 1, which will give us a balance factor of +2, which is invalid. The important thing again to note here is that the insertion is occurring under the right child of the node that has become unbalanced, and it is occurring in the left subtree of this right child. Our final case is illustrated over here. So here we are inserting a node Z, and we again update the balance factors from the newly inserted node to the root. So we update the balance factors for J, I, and C over there. Again, we will see that nodes I and J still have valid balance factors after they are updated. However, node C will have an invalid balance factor, and again, this will be a balance factor of +2. What's important to note here again is that the insertion has occurred under the right child of the node that has become unbalanced, and it is occurring in the right subtree of this right child over here. So those are the 4 cases that we need to deal with. And what we can then also see is that cases 1 and 4 are mirror images of each other. Basically, if we flip the tree along its vertical axis for case 1, then we will get case 4. Also, we can see that in a similar fashion, cases 2 and 3 are mirror images of one another. So what we will do now in the subsequent discussion is we will only deal with cases 1 and 2, and then cases 3 and 4 are simple modifications of cases 1 and 2. So the 2 cases that we'll now look at are cases 1 and 2. Case 1 is when we insert into the left subtree of the left child of n. So this is an outside insertion, as you can see over here, but it is under the left child of the node that has become unbalanced. Our second case is when we insert into the right subtree of the left child of n. So again, the insertion is under the left child of the node that has become unbalanced, but it's now in the right subtree. So this is then an inside insertion as opposed to an outside insertion in case 1. So let's start with our first case where we insert into the left subtree of the left child of node n, which has become unbalanced. So we can rebalance the tree by performing one single right rotation about the unbalanced node. So let's look at this in terms of an example over here. We have initially our tree without node A, and this is a valid AVL tree, but then we insert node A, and this insertion has occurred under the left child, and it's in the left subtree of the left child. We update the balance factors from this newly inserted node all the way up to the root, and we'll see then that, as I've previously mentioned, node G then gets an invalid balance factor. So these are the updated balance factors. We see that we have a balance factor of 0 for node A because it's a leaf node. Node B had initially a balance factor of 0 because it had no children, but because the insertion has occurred on the left branch, this means we need to decrease the balance factor by 1, giving us a balance factor of -1. This is still a valid balance factor. So now we move up to node C. Again, that had an initial balance factor of 0 because both the left and right subtrees had a height of 1, and we know that the insertion has occurred on the left branch, which means we once again have to subtract 1 from the balance factor, giving us a value of -1. Again, this is a valid balance factor. Now we get up to node G over here, which had a balance factor of -1, but we know that we've inserted on the left branch of G, so this means we need to subtract 1 from its balance factor, and this gives us a balance factor of -2, which of course then is invalid. So now we need to perform a rebalancing, and we're going to do that by performing a right rotation around the unbalanced node. So in other words, we're rotating node C about node G, which has become unbalanced. So if we perform this rotation, this is the tree structure that we end up with. So we see that node C has now moved into the root position over here. G has become C's right child, and the right child of C, which was node D over here, becomes the left child of node G, which has been rotated down. So now we can see we have a balanced tree again. All that then remains for us to do is to update the balance factors for the nodes that have been affected by the rotation. So what then happens is we update node C's balance factor to 0, and this is because node C has rotated up. The height of its right subtree has increased by 1, while the left subtree has remained unchanged. So this means that we then need to increase its balance factor by 1, giving us a balance factor of 0. If we look at node B, the balance factor doesn't need to change there, so it remains -1. And the reason for this is that nothing has been changed as far as its left and right subtrees go. If we look at node G, which has rotated down, we see that its balance factor now needs to be updated to 0. And this is because we have the right subtree, which contains the node H here, and the right subtree of node C, which has become the left subtree of G. Those two subtrees have exactly the same height, so therefore we add 2 to the balance factor of the unbalanced node, giving us a balance factor of 0. If we then finally look at node A, we see that its balance factor remains 0 because it is still a leaf node, and therefore there is no difference between the right and left subtrees in that case. So let's now consider case 2, in which we insert into the right subtree of the left child of node N, which has become unbalanced. So this is such a situation. We have our initial AVL tree over here, which is balanced, and now we are inserting node E. If we look at how our balance factors update, then we see that the new node that we've inserted has a balance factor of 0. The balance factor of D and C are both 1, which are valid balance factors, but when we get to node G, we have a balance factor of -2. So this is now an invalid balance factor, meaning that we need to rebalance our tree. So how should we go about this? Well, let's try the same trick that we used in case 1. So we will perform a single right rotation about the unbalanced node. In other words, we will be rotating node C about node G. So what happens then in this case? Well, this is the result of the rotation, and as you can clearly see, this tree is not a balanced AVL tree. So unfortunately, this single right rotation won't work in this case. We need a more sophisticated strategy. So how do we then actually go about rebalancing the tree if we have a case 2 situation? Well, the approach we'll use is that we'll transform case 2 into case 1, and we do this by performing a left rotation about the left child of the node that has just become unbalanced. So now we have a case 1 situation, and we can then simply rebalance the tree in the way that we've already described by performing a right rotation about the unbalanced node. So let's look at what this would look like in terms of a practical tree example. Over here we have the initial AVL tree, which is balanced, but then we add node E to this tree. So if we update our balance factors, then we get the following balance factors, as you can see over there, and we have updated node G's balance factor to -2, meaning that this node has now become unbalanced. So now what we need to do is perform a left rotation about the left child of the unbalanced node. So the left child of the unbalanced node is node C, and we need to perform a left rotation around that node. So in other words, we are rotating node D around node C. So the result of that then is this tree over here, and you can see that this corresponds to our case 1 tree, and over here are the balance factors updated for this tree rotation. So we can see that node G now still has a balance factor of -2. So we need to then rebalance the tree, and we do that then by performing a right rotation about the unbalanced node. So in other words, we are rotating node D around node G. So the result of that then is this tree on the right over here, which we can see is then a balanced AVL tree. Here are the updated balance factors for the nodes that have been affected by the 2 rotations, and we can see that they are all valid balance factors. Now, what's important to understand here is that the balance factor updates follow exactly the same pattern for any kind of insertion that falls within case 2. So we actually don't need to compute these intermediary balance factors over here. We just simply need to update them from this initial state over here, which is the unbalanced state, to these values over here, which represent a balanced state. Some students will implement the recomputation of these balance factor values by means of full tree traversals, but you can in fact compute the new values just based on the pattern of the balance factors for the nodes within the tree. So we now have a balanced tree, and what we saw was that we achieved this by performing a left rotation followed by a right rotation. So fairly often this operation in an AVL tree is referred to as a double rotation. So now we can finally summarize our 4 cases. And cases 1 and 2 we've dealt with on the previous slides. So in case 1, we perform a right rotation around the unbalanced node. In other words, we would rotate node C about node G. In case 2, we perform a left rotation around the unbalanced node's left child. So in other words, we rotate D around C, and then we perform a right rotation around the unbalanced node, which is node G. Now, cases 3 and 4 are mirror images. So case 3 is just simply a mirror image of case 2. So here we perform a right rotation about the right child of the unbalanced node. So in other words, the right child of the unbalanced node would be node I. We perform a right rotation around that, rotating H around I. And then we perform a left rotation around the unbalanced node, which is node C in this case. Then finally, our 4th case is a mirror image of our first case. So over here, we then perform a simple left rotation about the node that has become unbalanced. So in other words, node C has become unbalanced, and we rotate node I left about node C. So how will we actually implement these 4 cases? Well, we first of all need to start by taking our inserted node and computing the correct balance factors from that node all the way to the root. Now, as soon as we encounter an invalid balance factor, then we need to perform a rebalancing. So this happens if we encounter a balance factor greater than 1, in other words, positive 2, or a balance factor less than negative 1, in other words, negative 2. Now, if we have a negative balance factor, then it means that we have a left branch insertion that has taken place. And if the balance factor is positive, then we know that a right branch insertion has taken place. So let's look at our first case where we have a negative balance factor of negative 2, and we know that a left branch insertion has happened. What we then do is we compare the inserted value that we've just added to the tree, which we will represent as x, and we compare that to the value stored in the left child of the unbalanced node. Now, if x is greater than the value in the left child of the unbalanced node, then we know that we have inserted into the right subtree of the left child, and so we perform a double left-right rotation. If this condition is false, then we know that we've inserted into the left subtree of the left child, and so we perform a single right rotation. So next, let's look at the case where we have a positive invalid balance factor, in other words, balance factor of positive 2. So in this case, we have a right branch insertion that's taken place. So we then compare the value that we've just inserted, which is x, to the value stored in the right child of the node that has become unbalanced. So if the inserted value is less than the right child's value, then we know that we have inserted into the left subtree of the right child, and so we do a double right-left rotation. If this condition is false, then we know that we've inserted into the right subtree of the right child, and so we do a single left rotation. Now, what's important to understand here is that we stop after the first unbalanced node has been encountered and dealt with by means of one or more rotations. So, in other words, it's important to note that no ancestor nodes of the unbalanced node n need to have their balance factors updated. So this makes dealing with the insertion operation in an AVL tree very efficient. So let's look then at this tree to the right over here, and we've now inserted this node 4 into the tree. So we update then our balance factors, and we then need to determine which rotations need to take place. So what I would like you to do at this point is pause the video and update the balance factors for this tree, and then determine which rotation needs to take place. Alright, so we have a balance factor of 0 for the node that we've inserted because it's of course a leaf node. We have a balance factor of -1 for node 5 because it originally had a balance factor of 0, but we're inserting on the left branch, which means that we decrease that balance factor by 1, giving us a -1 value. This is still valid. So then we move up to node 6 that originally had a balance factor of 0, but we're inserting into the left branch, so therefore we update the balance factor to -1, and then we move up to node 9, and at this point we had a balance factor that was -1, but because we're inserting into its left subtree, we now update the balance factor by subtracting 1 from it and giving us a result of -2. So now at this point we have encountered an unbalanced node, and so we need to perform a rebalancing. So first of all, we need to look at our balance factor value, and we see that it is -2. So that means we are dealing then with case A over here, meaning that a left branch insertion has taken place. So then we need to compare our inserted value to the value to the left of the unbalanced node. So in other words, we are comparing our inserted value of 4, and we're testing to see whether it's greater than the value stored in the left child of our unbalanced node. Our unbalanced node is node 9, so the left child here then is 6, meaning that 4 is not greater than 6. So this test, in other words, then fails, so we go to this false outcome over here, and we then know that we have inserted into the left subtree of the left child of the unbalanced node. So this means we then simply perform a single right rotation about the unbalanced node. So this rotation will then move the node 9, which was unbalanced, down. It will then connect the right subtree of the left child as the left child of the node that is just rotated down, and then we rotate node 6 up and connect that to node 9, which has rotated down now. So at this point we have now created a balanced AVL tree. We don't need to look any further up the tree at any of the ancestor nodes above the node that has been unbalanced and that we've now dealt with by means of this rotation. Now that we've considered insertion into an AVL tree, we can move on to deletion. Deletion is somewhat more complicated than insertion, which we just discussed. So if we delete a node from an AVL tree, then we will perform a delete by copying. And as you've previously seen, this works by replacing the node that is being deleted with the rightmost node of its left subtree. So then we update the balance factors, and we start with the original parent of the copied node, and we move up towards the root. So let's assume that we have this AVL tree structure, and in this example we are going to delete node 3. So we then perform a delete by copying, and we do this by replacing the deleted node, its value, with the rightmost child of its left subtree. So its left subtree is over here, and the rightmost child is then the node containing the value 2. So what this then results in is that the value 2 moves up to replace 3, and we delete then the old node that previously contained the value 2. So now we need to update our balance factors from the original parent of the deleted node. So node 2 then was a child of node 1, so we then start by updating the balance factor of node 1, and that balance factor then becomes 0 because we have no children under that node. We then move up towards the root, so we're now at node 2, and the balance factor here is then updated to 2. So we can determine the updates that are required by looking at the depth of the node that is removed during the delete by copying operation. Right, so what happens then if the tree becomes unbalanced? Well, of course, in this situation, we can see the tree has become unbalanced because now we have a node with an invalid balance factor of positive 2. So what happens here then is for every unbalanced node that we encounter on the path to the root, we need to rebalance the tree using rotations. So what this means then is that several rebalancing operations may be necessary, unlike for insertions where we perform one rebalancing and then ignore the rest of the nodes on the way to the root. But how do we know then what rotations are needed? Well, specific combinations of the corresponding balance factors for our nodes will give us a good idea of what rotations are required. So there are a number of cases that we need to deal with as far as deletion in AVL trees goes. The first case is where we are deleting a value in the left branch, which causes this left branch to then become too small and then creates an unbalanced tree, which is indicated by an invalid balance factor. So in this case, we can see that we have a tree. It's initially balanced, but we are now deleting a node from this left subtree over here. This means that the height of this left subtree decreases then by 1, which means that it's become 1 shorter. So therefore we need to add 1 to the balance factor of node P in this case. So because node P already has a balance factor of positive 1, we then need to add 1 to it, which means that we now have a balance factor of positive 2, and this is an invalid balance factor. Now, additionally, a requirement for case 1 is that the right branch of the unbalanced node has to have a positive 1 balance factor. So we can see that that is the case over here. Node Q, which is the right child of node P, has a balance factor of positive 1. So in this case, we can then rebalance the tree by simply performing one left rotation about the unbalanced node. So let's see what this looks like. Over here we have a balanced AVL tree, but we are now going to delete node B, and this means we then need to update the balance factors from that node all the way up to the root. We don't perform any copying of nodes or values because we are deleting a leaf node in this case. So because we've reduced the height of the left subtree by 1, this means we need to increase the balance factor for node C by 1, which means we update this balance factor to 2 in this case. Node D still has a balance factor of 1 as it did previously. So this means we now have an unbalanced tree, and we know that this has occurred due to a deletion in the left branch by virtue of the fact that the balance factor for node C has become positive 2. So what this then means is we need to look at the right child of the unbalanced node, which is node D in this case, and we see that its balance factor is 1. This means we perform then a single left rotation around the unbalanced node. So in other words, we are rotating node D around node C. This is then the resulting tree over here, and we see then that we need to update the balance factors for nodes C and D because they've been involved in the rotation, and they are then updated to 0 values in both cases. This is the pattern that will always be followed in terms of updating these balance factors when this kind of rotation needs to be performed. The second case that we'll deal with also occurs when we delete in the left branch of a node, and this once again causes the left branch to become too small, which then causes an unbalanced node within the AVL tree. So here we have an example of this. This is a balanced AVL tree over here, and we are performing a deletion in the left subtree of node P. So in this case, we then have reduced the height of the left subtree by 1, and this means then that we need to increase the balance factor of node P by 1. So we increase it from positive 1 to positive 2, and this then indicates that we have performed a deletion in the left branch. Now we need to look at the right child of node P, and we see that its balance factor is 0 in that case. So this means we are dealing with case 2. So in order to correct this unbalanced AVL tree, we perform the same kind of rotation as what we saw in case 1. So we perform a single left rotation about the unbalanced node. So let's look at that in terms of this example over here. Here we have a balanced AVL tree, and we are deleting node B in this case. So again, we are performing a delete by copying, but we are deleting a leaf node, which means that we simply then delete the node in question. So this is then the resulting AVL tree. We then need to update all of the balance factors from the deleted node all the way up to the root, and then rebalance as necessary along that path. So we see because we've performed a deletion on the left branch of node C, we then need to increase its balance factor from 1 to 2, which means we now have an unbalanced AVL tree. So we then correct this by performing a left rotation around the unbalanced node. So the unbalanced node here is then C, and we are then rotating E around node C. So this is then the result of that rotation. We can see that we now have a balanced AVL tree. However, what sets this apart from case 1 is that the balance factors are updated differently. So we can see that after our deletion, node E had a balance factor of 0. After the rotation, we then subtract 1 from that value to give us -1, which is a valid balance factor. and then node C had a balance factor after the deletion of 2. Because we're rotating it down, we reduce its balance factor by 1, and so we have a balance factor of 1 for node C. Notice also that the balance factors for nodes D and F don't change after this rotation has taken place. The third deletion case again involves a deletion in the left branch of a node, which causes the left branch to become then too small. So we can see that again in this situation over here. We have a deletion that occurs within this branch, and that reduces the branch's height by 1, which means then that we need to update the balance factor of P by adding 1 to it, producing a balance factor of positive 2. So at this point, we then have an unbalanced node which needs to be corrected by means of rotations. And for this then to fall under case 3, the right child of the unbalanced node, in other words node Q, must have a balance factor of -1, and the left node of that right child, in other words node R, must also have a balance factor of -1. So if this is the case, we know that we're dealing with a case 3 deletion, and we correct this by means of a double rotation. So we perform a right rotation about the right child of the unbalanced node, and then a single left rotation about the unbalanced node. So let's look at what this would look like in an example tree. Over here we have an AVL tree which is balanced, and we are going to delete the node containing the value 1 from the tree. So we simply then perform a deletion by copying, which means that we copy then the value 2 into the node that has had its value deleted, and we then delete the node that we have copied from. So this is the tree that results from this deletion, and we then need to update the balance factors of node 2, which will then update to 0 because it has no children, and then the balance factor of its parent node will be updated by adding 1 to its original value, giving a balance factor of +2. So this of course then is an unbalanced situation due to a deletion in the left subtree of node 3, and we then look at the right child of this unbalanced node, in other words node 9. We see that its balance factor is -1, so we then look at that node's left child, which is node 6, and we see that its balance factor is also -1. This indicates that we're dealing with a case 3 deletion, so now we need to perform a right rotation around the right child of the unbalanced node. So this is the right child of the unbalanced node, and we now need to perform a right rotation around that, so we are rotating node 6 about node 9. So this is the tree that then results from that rotation being performed, and then finally we perform a left rotation about the unbalanced node. So the unbalanced node is then node 3, and we are performing a left rotation around that. So in other words, we are rotating node 6 about node 3. This is then the final result of that rotation, and we can see that we have a balanced AVL tree once again. Now, the important thing also to note here is how the balance factor values are updated as a result of these rotations. So we can then see that the node that became unbalanced due to the deletion had a balance factor of 2 that has now been updated to 0. The right child of the unbalanced node had a balance factor of -1, as we can see there, and that balance factor is then updated to +1. And then finally, the left child of the right child of the unbalanced node, in other words, node 6 in this case, had a balance factor of -1 that is now updated to 0. Let's now look at the fourth deletion case, and once again here we are dealing with a deletion in the left branch, which causes an unbalanced node. However, in this case, the right child of the unbalanced node must have a balance factor of -1, and the left child of this right child must have a balance factor of +1. So we can see that illustrated in this example over here. Here we have our balanced AVL tree. We are deleting from this subtree, which reduces its height by 1. This means we need to then add 1 to the balance factor of node P. And because its balance factor was +1, we now have a balance factor of +2, which is an invalid value. So this means we then need to perform a correction to balance the tree again for this unbalanced node. So we now need to look at the right child of the unbalanced node. We see that its balance factor is -1, and the balance factor of the left child of this right child is +1. So this means we are then dealing with case 4. So again, we perform a double rotation, and this is the same double rotation as we performed for case 3. So a right rotation about the right child of the unbalanced node, and then a left rotation about the unbalanced node. So let's look at what this looks like in terms of this example over here. Here we have a balanced AVL tree, and what we are now going to do is delete the value 1 from this tree. Well, we are performing a delete by copying, so this means we copy this 2 value into the node from which we've deleted our value, and then we delete the node that we copied from, so that gives us this AVL tree over here. So because we've deleted then in the left branch, we then need to update the balance factors for the nodes. So the node that we copied the value 2 has a balance factor of 0. And because we deleted then in the left branch of node 3 over here, its balance factor is updated to 2 by adding 1 to the original balance factor, and now we have an unbalanced node. So we now look at the right child, which has a balance factor of -1, and the left child of that right child, which has a balance factor of +1. This means that we're dealing with case 4, so we perform then a double rotation. First of all, we perform a right rotation about the right child of the unbalanced node. So we are rotating 6 about 9. So that then produces this AVL tree over here, where 6 has been rotated up and 9 is lower in the tree. And then we perform 1 left rotation around the unbalanced node. So again, the unbalanced node is this node 3 over here. So we perform then a left rotation of node 6 about that unbalanced node. The result of that is then this AVL tree over here, but what's important to note is that the balance factors of the affected nodes are changed differently compared to case 3. So we can see that after our deletion, the unbalanced node had a balance factor of 2 that is then updated to -1 in this case. We see that the right child of the unbalanced node had a balance factor of -1, and that is updated to 0 after the 2 rotations have been performed. And then we have the left child of the right child of the unbalanced node, which had a balance factor of 1, that is now updated to 0. So let's finish off by looking at some implementation details related to deletion cases for AVL trees. Well, what we saw with the 4 cases that we've just discussed is that cases 1 and 2 are dealt with in the same way, and they both require a single rotation. So you can do this with a single if statement that handles both cases. The only difference between the 2 cases is how the balance factors are updated. Cases 3 and 4 also both require the same kind of rotation, in this case a double rotation. So again, you can deal with these 2 cases via a single if statement. The only difference is how the balance factors are updated. Now, with cases 1 to 4, we dealt with deletions within the left branch of an unbalanced node. So there are 4 more cases that deal with deletions in the right branch of an unbalanced node. And these are essentially then mirror cases of the 4 cases that we've just discussed. So what this means is there are 8 distinct cases that we need to take care of in total. So what I would like you to do as an exercise is work out the remaining 4 cases and how they will be dealt with by means of rotations. Once again, just to reiterate a point that I made earlier, it is very important that you perform all of the corrections that are necessary when a value gets deleted from an AVL tree. So you will keep updating the balance factors up the tree until you encounter an invalid balance factor. You'll then deal with that by means of a single or a double rotation. But then it is important that after that correction takes place, you continue then updating the balance factors up the tree and possibly performing further corrections by means of single or double rotations. All right, so that concludes this lecture. And we will then continue with our discussion on binary trees in the next lecture, where we will look at self-adjusting trees.